continuing having a look at goodness of fit, we're now going to move on to having a look at the normal distribution. So for goodness of fit with the normal distribution, we need to find or use a mean and standard deviation to find the probability of certain outcomes, and then multiply that by the number of observations that we've got. The test, we care about the mean, the standard deviation, and the number of observations. So if we are having to use the data to find the mean and standard deviation, then the number of groups after, then the degrees of freedom is going to be the number of groups after pooling minus 3. So this is when we have to find the mean and standard deviation using the midpoint of the intervals and the frequencies. If we are given the mean and standard deviation, so we're only given one of them, then the degrees of freedom is going to be the number of groups after pooling minus 2, because one of those is going to be fixed. And if we are given the mean and standard deviation, then degrees of freedom is going to be the number of groups after pooling minus 1. So to start off with, we're on minus 3, and for every extra piece of information we've been given, we take one off what we would be taking off the degrees of freedom. As the normal distribution tails off in both directions, we need to ensure that the first interval goes down to minus infinity and the last interval goes up to infinity. So we need to ensure that we have our tails at either end. And the normal distribution is also a continuous distribution. So if we have been given discrete data, we have to make sure that that is continuous by taking the midpoints between the two intervals as the new start and end points for those intervals. So we've got an example here. So here we've got the following table summarizes the percentage fat content of a random sample of 150 hamburgers. So that is my sample size. We can also add the frequencies up and we should get 175 as well. And we're trying to just see if the normal distribution fits here. So we haven't been told a mean or a standard deviation that we're trying to see fits with this distribution, so we're going to have to calculate it for the data. So the first thing that I would point out is that the ends of these intervals are not the same as each other, which means at the minute I have discrete data and not continuous data. So the first thing I'm going to do is I'm going to change the beginning and end points of these intervals to make it so that I have continuous data. So this one here is then going to go from 25.5 to 27.5. This one from 27.5 to 29.5. And we did do this in AS when we were having a look at finding averages to begin with. And we talked about how we need to have continuous data. We need to have continuous data because what we're actually doing is a bit like interpolation. So we need to have continuous data for that. So I'm changing the start and end points of my intervals so that then I have my data continuous, because like we just said, the normal distribution is a continuous distribution. Because I haven't been given the mean or standard deviation, that means I'm going to have the midpoints to be able to find my mean or an estimate for my mean. So remember that if you can't decide what the midpoint of two values is, then you can always go to the normal part of your calculator and we can add together the two endpoints at the intervals, and then we can divide that by 2. And that would give us our midpoint. So the midpoint for this one is 26.5. This one here would be 28.5. This one would be 30.5. This one would be 32.5, 34.5, 36.5. And then this one here, which goes from 38 to 40, is actually going to be 39. So just be careful that you don't fall into the trap. If you've got different sized intervals, it might not be as easy to find the midpoints. So then to find our estimate for the mean and standard deviation for this question, I'm going to go into the statistic part of my calculator, delete what I've already got in there, put my midpoints into list 1, put my frequencies into list 2. Then I'm going to go to Calc, check that my set, so I need this to say list 1, list 2, because I put my data into list 1, and I am putting my frequencies into list 2. Then we're going to go into one var. So we are testing if this data here fits the distribution. Oops. With a mean of 32.5 to 3 significant figures. And a standard deviation, well, this is a sample. I know that the standard deviations are almost the same, but this is a sample of hamburgers. It's not the whole population of hamburgers, so it's the sample standard deviation that we would be using. So it's the SX. So that's going to be 2.93 to 3 significant figures. And remember, it's actually the variance that we put into our distribution. So my H naught here is actually just going to be that the normal distribution is a good fit because we haven't been given any parameters. So I don't need to say with a mean of something and a standard deviation of something, because we're just trying to see if the normal distribution is a good fit. And then our H1 will be that the normal distribution is not a good fit. So then we're having to find our probabilities. Now remember that we need to make it so that our data goes down to infinity and up to infinity. So instead of having my first category as 25.5 going up to 27.5, my first category is actually going to be that we're looking at less than or equal to 25.5. Whoops. All the other intervals are still going to stay the same, so we're going to have from 27.5 to 29.5, just writing it this way to make it a bit quicker, 29.5 to 31.5, 31.5 to 33.5, 33.5 to 35.5, 35.5 to 37.5, and then 37.5 to 40.5. And then because we need it to go on forever as well, we need it to go up to infinity, we're also going to have x is greater than or equal to 40.5. And remember, because the normal distribution is a continuous distribution, the probability of it being greater than or equal to 40.5 and the probability of being greater than 40.5 are going to be the same. So then I'm going to go into my dist norm NCD. For the first one, because we're looking for the lower limit, my lower is going to be minus 9. My upper is going to be 25.5. My standard deviation is 2.93 from what I put up here. So 2.93. And my mean is 32.5. So that gives me 0. So these are my probabilities. 0.0084453. Then we're going from 25.5. So my lower is 25.5 to 27.5, which gives me 0.0355139. Then we're going from 27.5 to 29.5, which gives me 0.10898449. Then we're going from 29.5 to 31.5, which gives me 0.21349659. Then we're going from 31.5 to 33.5, which gives me 0.2671194. Then we're going from 33.5 to 35.5, which gives me 0.21349659. Then we're going from 35.5 to 37.5, which gives me 0.10898449. Then we're going from 37.5 to 40.5, which gives me 0.04079582. And lastly, our lower would be 40.5. Our upper would be a really big positive number, which gives me 0.0031631. Now, we can notice something about these probabilities. Something that's quite interesting is that because it's normally distributed and because in the middle here all our intervals are the same size, we can see that we do have that symmetry that we would be expecting from the normal distribution. Okay, we can see that we're going up 0.108, 0.213, 0.267, then back down to 0.213, then down to 0.108, okay? And we can see that here, but when we get to this last interval here, because that's slightly different size to the other intervals, we can see that that doesn't carry on the symmetry for the last two. So do always be careful. Don't just assume that you are going to end up with symmetrical probabilities so that once you start going back down, oh yeah, they're all going to be the same. Do still find the probabilities because they could be different. So then to find our expected values, we're going to be timesing by the number of pieces of data we have. So like I said, you could add up the frequencies, but we were told here that we had 175. So we're going to be timesing by 175. So into the normal part of our calculator, we're going to have 0.0084453 times 175, which gives us 1.477925. So that means that we already know that we're going to have to do some pooling. So we've got 0.0355139 times 175, which gives us 6.2148785. Then we have 0.108984449 times 175, which gives us 19.07228575. Then we have 0.2134969 times 175. Whoops, sorry about that. Which gives us 37.36190325. Then we have 0.2671194 times 175, which gives us 46.7459895. And I don't need to put these next two into my calculator because, as I just pointed out, they are the same as what we had previously. So to save a bit of time, because I'm doing the same calculation, I can copy them down from above. Then we have 0.0407952 times 175, which gives me 7.1392685, and lastly we have 0.0031631 times 175, which gives us 0.553525. So we're going to have to pull together our first two intervals and our last two intervals, which means that this is going to become less than or equal to 27.5, and this one's going to become greater than or equal to 37.5. So we need to go back and find those new probabilities. So in stat, dist, norm, NCD. For the first one, my lower is going to be minus 9. My upper is going to be 27.5, which gives me 0.04395894. And then for the last category, we've got from 37.5 to a really big positive number, which again gives me 0.04395894. And that's what we would be expecting, because remember we talked about the symmetry and we talked about how because of the intervals at the end that we lost that symmetry, but because then we're pooling those together we regain that symmetry. So I was expecting to end up with the same values there. So then we have to find our new expected values. So then we're going to have 0.04395894 times 175, which gives me 7.692845 for both of these. All these other expected values are going to stay the same. So the observed values as well, because actually this first interval that I created to make it so that the normal distribution was tailing off in both directions had a frequency of 0. That means that this first interval is still going to only have a frequency of 7, then 22, then 36, then 45, then 33, then 28. And again, for this top interval here, the interval that I created had a frequency of 0, so that's going to stay the same as before as well, which gives me 4. So in the stat bit of my calculator, I'm going to delete what I already have in there. Remember that your observed values go first. So we've got 7, 22, 36, 45, 33, 28 and 4. Then we have our expected values next. So they were the 7.6928145, then 19.07228575, then 37.36190325, then 46.7459.895, then back down to 37.36190325, and then our 19.07228575, and then lastly 7.6928145. Then remember that we're going to test chi, goodness of fit. We talked about the degrees of freedom before. So the degrees of freedom is the number of groups that we have after pooling, which is 1, 2, 3, 4, 5, 6, 7. And usually we take off 3. If we were given any information, then we take one off what we were taking off. But here we weren't given the mean and we weren't given the standard deviation, so I'm going to have to take off 3, which gives me a degrees of freedom of 4. That gives me a chi-squared value of 7.74. That's the test statistic. The critical value, looking at page 20, we weren't told what significance level to use. No. So that means we're looking down from 0.95, we're looking across from 4, and that gives me 9.488. So then as the test statistic is smaller than the critical value, we accept H0 at a 5% significance level. There is insufficient evidence to suggest the normal distribution is a good fit. Sorry, is not a good fit, because we're writing about H1. Okay, on to another example. So here we have some more data. It believes that the following data follows normal distribution with a mean of 12 and a standard deviation of 2, and we're trying to test this at a 10% significance level. So our H0 this time is going to be that the normal distribution or model with mean 12 and standard deviation 2 is a good fit. And then our H1 is going to be that the normal distribution with mean 12 and standard deviation 2 is not a good fit. So this time our data is continuous. We can tell that because the intervals are ending and starting at the same points. Also, we already have that the data is going up and down to infinity, so we don't have to change anything with this data. So we've got x is less than or equal to 8, then we're looking between 8 and 10, 10 and 12, 12 and 14, and then greater than or equal to 14. So we're going to have a look at our probabilities. So back out of here, dist, norm, NCD. So for the first one, my lower is minus 9, my upper is 8, my standard deviation is 2, and my mean is 12. So that gives me 0.0227513. Then we're looking between 8 and 10, which gives me 0.13590512. Then we're looking between 10 and 12, which gives me 0.34134474. Then we're looking between 12 and 14, which gives me 0.34134474. And then we're looking at greater than or equal to 14. So 14 in the lower, a really big positive number in the upper, and that gives me 0.15865525. So then we need to find our expected values. So we need to add together our frequencies to know that what we're timesing by. So we've got 3 plus 5 plus 7 plus 7 plus 6. Which gives us 28. So we're going to times all these values by 28 to get our expected values. So that gives me 0.2275013 times 28, which gives me 0.6370036. So I know I'm going to have to do some pooling. Then we've got 0.13590512 times 28, which gives me 3.8053436. Then we have 0.34134474 times 28, which gives me 9.55765272, which is going to be the same for the next one as well, because we've got the same probability for those. And then lastly, we've got 0.15865525 times 28, which gives us 4.442347. So we're going to have to do some pooling here. We're going to have to pool together these first three groups here and the last two groups here. So this first category here is going to change to being less than or equal to 12, and this one here is going to change to being greater than or equal to 12. So back into dist, norm, NCD, and hopefully this won't be a surprise to you when you get this answer here. So our lower is minus a big number, our upper is 12, and we get 0.5. Okay, because it's halfway. The mean's in the middle. It's a symmetrical distribution, which means the mean equals the mode equals the median. So that means that when we times in that to find our expected values, we'd get 14 and 14. For our observed values, that means that I'm pulling together these top three here, which would give me 15, and I'm pulling together these bottom two here, which would give me 13. So then we're going into back here, deleting what we have in the calculator. Our observed in list 1, so 15 and 13. Our expected in list 2, so that's 14 and 14. Going into test, chi, goodness of fit, and the degrees of freedom this time, well, the number of groups that we have after pooling is 2. And like we said, usually we'd take off 3. But in this question, I was given both the mean and the standard deviation, which means that they no longer vary with the data. So that means I would no longer take them off, which means that instead we only end up taking off 1. So you take off 3 if you're given nothing, you take off 2 if you're given the mean or the standard deviation, and you only take off 1 if you're given the mean and the standard deviation. So then that means that my degrees of freedom is going to be 1. So my chi-squared value is 0.143 to 3 significant figures, which is my test statistic. My critical value, we were told to use a 10% significance level, which gives me so this is page 20 again, 2.706. So then as the test statistic is smaller than the critical value, again we would end up accepting H0 at a 10% significance level. There is insufficient evidence to suggest the normal model or distribution with mean 12 and standard deviation 2 is not a good fit. Now in reality, if you were to talk about pros and cons of this test, I mean, we've just split the data in half and said, yeah, about halves on each side in the end of it, okay, which isn't a very good test. And also, if you think about the number of observations we only had 28, so we didn't have a lot to look at, which is why we ended up having to pool so many groups together. So hopefully that clears up how what we take off our degrees of freedom depending on what information we've been given in the question for the normal distribution. Please try the Now You Try questions, and thank you very much for listening.